Okay. So for audience in the Zoom, could you hear us?
Yeah, we can hear now.
Great, thank you. Okay, sorry about the small interruption. Thank you, Jihei, for making it work. Okay, so where were we before? I was showing you that if we have this even metal, right, and then if we run diffusion equation on this even metal, over time, you will see that there is a very strong rotation symmetry in the diffusion dynamics. But if the model is not even, right, in this case, we have an uneven metal, and when we run the diffusion dynamics on this uneven metal, then this diffusion heat will actually be asymmetric. So it does not have the rotation symmetry as before. And this type of symmetry breaking is very common in practice due to either the physics or the observational noise. So we need to relax the definition of symmetry to have approximate symmetry. And the way we relax it is actually very simple, right? Remember, if we're learning a function from input to output, and we have a group G, so the representation of G is denoted as rho. So in this case, in the case with perfect symmetry, then we know f of G is equals to G of f, right? But if the model doesn't have perfect symmetry, then we can simply say the gap of these two transformations is upper bounded by a small constant epsilon. So in this case, depending on how much epsilon we have in the model, we can break the symmetry to different amounts. So then how can we implement this approximate symmetry in practice? There is the earlier version of equivariant convolution called group convolution, and this is a direct generalization of convolution to any groups. So if you're familiar with the convolution for translation group, then this is just simply say, I can compute the inner product between the input feature and the kernel by picking convolving over every element in the group. So this kind of group convolution is perfect, and it's also very slow because we need to compute the summation over all the elements in a group. So if a group is infinite or continuous, then it is not possible to compute the group convolution. But we can still relax this group convolution to have relaxed the group convolution. So the key idea of introducing symmetry breaking in group convolution is that we can, instead of using one kernel that is shared across all the input, we can actually have different kernel bases that then this actual kernel is a linear combination of kernel bases. And then the weights here, or the coefficients of this linear combination W, is actually dependent on the input. So because of this coefficients now depend on the input, then it's no longer perfectly equivariant. So depending on how many basis function or kernels L we put into this equation, we can break the symmetry by different amounts. If we have L equals 1, then this equation will reduce to the perfectly equivariant case. And if we have a very large L, then the relaxed G convolution will be closer and closer to the model without any symmetry. So this way give us, yes.
Sorry, what was the benefit of relaxing the symmetry again? Doesn't that go against what you said earlier about one of the goals being to increase generalization?
Yeah, so because the motivation is that we want to bridge the gap between simulation and real world. Okay. Because in real world, we often don't have perfect symmetry.
Okay, thanks.
Great. And then we can also compute similar type of relaxation for this type of steerable convolution, equivariant convolution. So this equation that we showed before is a more efficient way to compute equivariant networks. So instead of computing aggregation over group elements, we're computing the equivariance by first compute this representation of the group as a left and right multiply using matrix multiplications. And then we have the kernel that need to be solved using these linear constraints. So we can similarly relax this equivariant convolution using the same idea. So we have, instead of one kernel K of X, we can have a linear combination of kernels that K of L with the coefficients WL that are dependent on the input data. So this capital L, which is a number of kernel bases we use in equivariant convolution, allows us to change the amount of symmetry breaking in the architecture. So just to test this idea, right, we constructed the simulated case. So we have the ground truth turbulence. So this is it's the flow with external forcing. So this external forcing will break the symmetry by different amount. So this is over time from t equals 1 to t equals 20. We can change how much force we apply to this turbulence, and that will break the symmetry by different amount, right? So what we can see here is that if we use a convolutional neural network, so this neural network doesn't have rotation symmetry, and you can see that the prediction of this convolutional network is very blurry. But if we use a perfectly rotation equivariant network, the E2CNN model, then it does learn the small scale behavior compared to the ground truth, right? But at the very end, when t equals 20, the direction of the turbulence is actually completely wrong. So the turbulence should curve to the right, but then the perfect symmetric model is predict the turbulence to curve to the left. So that shows that when we have models that are overly constrained to this symmetry, then sometimes it has a negative effect. So the symmetry in the model doesn't match the symmetry in the data due to symmetry breaking, right? And in contrast, the relaxed model, relaxed steerable equivariant network are steer. It can capture the small scale behavior quite well. And more importantly, it can predict the direction of this turbulence accurately compared to the ground truth. But then there's still limitations in this model, as you can see, that when it goes to t equals 20, the predictions of relaxed equivariant networks becomes a little bit blurry. So we hypothesize that is because this linear aggregation of kernel bases can have some strong assumptions on the modeling part. Okay, so this is type of the ideal picture we want. So we're measuring the data equivariance error, which quantifies how much symmetry is in the data. Zero error means perfect symmetry. Large error means no symmetry. And this y-axis is a model equivariance error, which quantifies how much symmetry is in the model. And this can be controlled, the y-axis can be controlled by learning this different kernel bases in our model. So we can see that for a perfectly equivariant network, the E2CNN, it actually doesn't matter how we change the symmetry in the data, it always have the same performance. So in other words, the model is not adapting to the symmetry in the data. But on the other hand, we have our model, the relaxed steerable CNN. So in red, you can see that it tried to adapt the model quite well, but still very far from the optimum case, right? So the optimum case in this dashed line. So the optimum is, basically the same amount of data is reflected in the same amount of model. And so we still have some work to do to bridge this gap. Yeah.
What do you think is required to make a more adaptive model?
I think one is definitely data, right? So if you have enough data to learn, then the model have enough information to figure out the right amount of symmetry. The other one is to improve the model flexibility. So in this case, we're actually fixing the group elements, but just changing the amount of symmetry breaking within that group. You can also imagine models that are more flexible, which can not only adapt to the amount of symmetry breaking, but also can adapt to different groups. Because then you can have data that contain multiple group symmetry, right? Then if you have a model that can automatically detect the right group, it will be more flexible. Yeah, great question. Yeah.
You said there's a force being applied. Is that force time dependent as well, or no?
It's not. It's a time invariant quantity.
But that would, if it's time dependent, that would complicate things further.
Of course, yes. That's a great thought. Okay, then we apply this to the supersonic jet flow. This is the real experimental turbulence data from NASA. And this is taken as a video. So we have cameras. You have 7 different cameras taking pictures of this turbulence. And then it measures the velocity field when these jets pass through this tunnel. So it creates this time resolved video of the turbulence. And then we try to predict the future evolution of turbulence, especially near the nozzle region. So we tested two cases. One is future generalization. The other one is domain generalization. So future generalization means that we take small patches of this turbulence and try to forecast into the future. Domain generalization means that we take different areas of the turbulence and predict a different spatial domain. We can see that compared to a perfectly equivariant model, E2CNN, the relaxed version is quite better, much better than the strictly equivariant networks. So that shows that, by relaxing the symmetry, we can improve the prediction performance. So this is the prediction error visualized for this image over time from t+1 to t1 equals 1 to t equals 10. So this is the error, right? So the white is the best, the white is 0. And then we can see the predictions from the relaxed steerable compared to the baseline. This is another version of relaxed steerable CNN. And then this is a perfectly equivariant model. So you can see that the error is the lowest for the relaxed version. Okay, so this is some work that we did about incorporating physics into deep learning models. As I mentioned, we have many challenges among deep learning for climate forecasting. But let me just briefly talk about this work since we're at the time. And this work is trying to quantify uncertainty for the climate data. So we have this type of data collected from different resolutions. This is also some work we're collaborating with Aziz. Right, so the idea is that if I have simulation data from climate, discretized at different resolutions, so we have coarse grid data and we have the fine grid data, right? The coarse grid data is very cheap to obtain, but they're not accurate enough to describe the climate process. And then we have the fine grid data, which is very expensive to obtain, but they contain a lot of information. The question here is, can we combine different type of data to have the trade-off between computation and information? And that's the idea behind multi-fidelity modeling. So in fact, multi-fidelity modeling has been studied intensively in engineering field, right? So if we have this climate model, right, the global climate model, this is in 150 to 300 kilometer resolution. And then this is the coarse grain model. And then we have a regional climate model, which is a 12 kilometer resolution. So have these two different fidelity model is of different accuracy and different computation. So how can we learn the model, again, a deep surrogate model, to emulate the dynamics of this phenomenon, but then by combining simulations of a different resolutions or different fidelity? So in engineering applications, this is a tool that has been widely used called Gaussian processes. So Gaussian processes is often used to provide uncertainty for the prediction. And the idea is that you have a function which is in this solid line, the wiggly line, but then you assume that every point on this function is a Gaussian distribution. So in total, you have infinite number of Gaussian distribution. You impose the prior distribution over functional space, and that becomes the Gaussian processes. So Gaussian processes is flexible, right? You can see that it can model pretty much any function. It also gives uncertainty to have this kind of confidence interval around prediction. But a limitation in Gaussian process is that it's extremely expensive to compute. And then when we have very large data sets, like in a climate case, GPs will have computational bottleneck. So naturally, there is this idea of combining deep learning with Gaussian processes. And this is a work called neural process. So the neural process idea is that instead of manually designing the kernel function in Gaussian processes, we can use a neural network to learn the kernel function, very similar to the turbulent flow net idea that we presented earlier. So in a neural process, we have the input data XC and output YC. These are the conditions, the grounding points. And then we use a neural network to learn the latent variable that can be used to guide the prediction of on-sync point or target points. So we replace explicit kernel in GP to a data-driven prior. So it's very similar to a variational autoencoder kind of framework. So we have the data from input and output pairs. We use the encoder to infer the data-dependent kernel function R. And then in the end, we aggregate the kernel function to reach the latent variable Z and use this condition latent variable Z, we can decode into the prediction of the target set. So this is based on variational autoencoder, and naturally we can optimize this model using a lower bound of likelihood called the evidence lower bound, or ELBO. So unfortunately, this neural process itself only provides the latent information in one fidelity. But here we wanted to model data from multiple fidelities. And then how can we do that? Where we actually designed a new neural process model based on the hierarchical idea. So in a single fidelity case, as I showed before, if I have some training data, input and output pair, we can use this input data, training data, to learn latent variable Z, and this latent variable combined with the testing data input will give me the prediction. And then there is an extension of the single fidelity neural process called multi-fidelity neural process. So this idea is just simply concatenate the new higher fidelity data together with lower fidelity data to infer the latent variable Z. But then this way doesn't have any information sharing from low fidelity to high fidelity. And then the high level idea behind our model is to use multiple latent variables, ZL, which stands for the latent variable in the lower fidelity, and ZH, which is a higher fidelity latent variable, and allow these two hierarchies to talk to each other. So then we have information sharing between different fidelities. Yes.
Do you happen to know off the top of your head the big O for Gaussian versus neural versus your multi-fidelity NP?
Yeah, I mean, usually for like Gaussian processes, because of matrix inversion, is like cubic, right? But there is much faster methods like sparse Gaussian processes that can do like n squared times k, where k is the number of sparse points. And then for neural processes, because it's a neural network model, so when we do this kind of forward inference, it's only linear in terms of number of points. Right? But then training of this model can take some time. Yeah, Laura. I cannot hear you.
Do you have any uncertainty quantification with the new algo?
Yes, because this model is probabilistic. So the uncertainty, so everything I draw here is a random variable. Yeah, great question. Okay, so the way we achieve the uncertainty is through ancestral sampling, which I will not go into details. So this is on the data that we experimented with climate data. So we have this region in South America, and we have low fidelity data coming from RCM, and we have high fidelity data which comes the low fidelity data comes from GCM, and the high fidelity data comes from RCM. So we want to combine these different data to predict the climate. And then here is basically the prediction realization from our model. So we can see that when we predict 6 months ahead, where you can see the hierarchical model, this is in terms of error. So the more brown, the better. So this is the prediction of error. So when we forecast into the future, the model from this hierarchical modeling can have very accurate prediction with almost zero prediction error. But then when we look at the Gaussian process models, it has accurate prediction within this region, but it has very poor prediction on the boundaries. Okay, so I think that's probably time for us to conclude. We also have, the uncertainty quantification metrics like log likelihood and the ELBO in our paper. I will not show here. So I talked about some work in physics-guided deep learning and talked about TFNet, that learnable CFD operator for turbulence flow forecasting, the Equivariance networks that incorporate symmetry into deep learning for tackling distribution shift. And we talked about a relaxed version of Equivariance network that can bridge the gap between simulation and real world. And then I talked about this hierarchical neural process for multi-fidelity modeling that also allows uncertainty quantification. So there's a lot of work that needs to be done here. As I mentioned, the discovery of symmetry is a very exciting direction that we're currently exploring, generalization to irregular mesh or graph networks or active learning. We also have some projects going on with Bayesian active learning to smartly query data instead of training data from offline. Okay, so you can find the code and data on my website or follow me on Twitter. Here is the funding agencies for supporting this work. Thank you.
Thanks so much, Rose. A fantastic talk. Any questions for Rose?
Yeah, hi. So I was wondering in the multi-fidelity uncertainty quantification, why you need the low fidelity data, because it's already contained in the high fidelity data, right? It's just a downsampling of the data. So I'm wondering what, if you know what it actually brings to the model and why.
I think only one can be on it.
Yeah.
Oh, hi. Hi. Okay, great question. So yeah, just to clarify, like the low fidelity data is not a downsampled version of the high fidelity data. So low fidelity data comes from a different model. So in our case, the low fidelity data is coming from the global climate model. So that's the set of differential equations discretized at different step size as the high fidelity model. And the high fidelity model in our case is the RCM. So they're different models. They're not one downsample from each other. Yeah. Because otherwise it will be redundant information. Yeah.
Hi, at the beginning of your talk, you talked a bit about what motivated you to sort of start this line of work. Can you go back to that? Were you in conversation with particular groups of people who were trying to solve a problem? What spurred this particular area of your research?
Which area?
So at the beginning, you said you were zooming in on this question around turbulence and how to model. So were you motivated because someone came to you and asked you to pursue this line? I don't remember what you said exactly at the beginning.
Oh yeah, just because my student did their internship at Lawrence Berkeley National Lab, and there is this group of scientists. Most of them are climate scientists, so they're interested in developing deep learning models to accelerate, to speed up turbulence simulation, or more general climate models. So then we thought about to study a much more fine-grained problem, like a smaller problem, as a prototype. And that is basically the start of this project. And we learned about a lot of things in turbulence modeling throughout the collaboration. And then we moved towards like incorporating other physical constraints like symmetry. And the uncertainty quantification problem is also something we learned from our collaborators. And we learned that, uncertainty is very important. And that also creates challenge for deep neural networks because deep neural networks are mostly not the probabilistic.
Thank you.
Yeah, Laura.
Right, thanks, great talk as always. So for the multi-fidelity model, so you mentioned that compared to Gaussian processes, then this is actually kind of faster to some extent.
It's not only faster, the results are also better. So that's something quite exciting. So you can see that this is the error plot, right? So the brown, the better. So when we forecast further, the error also becomes smaller.
And you've done that, and you've done that for temperature, correct?
This is for temperature,
Yeah.
correct?
Have you tried other variables that are a little bit more turbulent and harder to get?
Oh, we haven't. We don't have the data. Yeah, this data set was provided as an open source data set for multi-fidelity modeling following a group in Amazon research. But if you have like exciting data, I would love to try it.
Yeah, it's very impressive. Thanks.
Huh?
Aziz and your group are trying on the.
Oh, yes. Sorry about that. I forgot. Like Aziz is doing some wonderful work. I think Aziz should be a better person to talk about that. Actually, do you want to comment on this?
Yeah, so we're actually trying some standard CAM parameterization for cloud formation. I've been working on a heating tendency, and then we'll tackle the moistening tendency. And we're also trying another approach based on randomized prior network, which is an ensemble method. It's still work in progress. And back to the question about the multi-fidelity, what we're trying to prove now is that we want to prove that relying on a multi-fidelity model improves a single fidelity model, because people can say, if I have some high fidelity data, I can just work on that and come up with the parameterization. We want to show that when you use also the low fidelity data, you improve the high fidelity parameterization. So yeah, that's in progress.
Thank you both.
Awesome, thank you.
I can't speak loud. Like in
Yeah,
this
the
panel.
the mic is coming.
Great talk, thanks so much. So, like in this panel, why the third panel on the top has a larger error compared to the last one, while it's a shorter prediction, like shorter time prediction?
Yeah, very good observation. So I think it has something to do with our input length. So when we train our neural process model, we need to condition on the context set. So that is how long we are actually conditioned on the past is a hyperparameter we tune. I think I think my hypothesis, but we don't exactly know why. But the hypothesis is because the hyperparameter we land is 3, and then the model is learned this like short-term dynamic of 3. So then after 3, there is a sharp drop in prediction performance. Yeah.
Can I ask a second question?
Sure.
So for the like the first part of your talk that you were showing the filters, that you were learning the filters, how do you set like the size of the filter? Like, for example, in a space, how far it could see, or like in time, how far it could see into the past?
Yeah, I mean, that's an excellent idea. So in our case, we're not learning the size of the filter. It's actually non-trivial to learn the size of the filter because the size of the filter is discrete. So it's a discrete variable that's not differentiable in deep learning. So there was a recent paper actually in iClear about learning the size of the filter in the convolutional neural network. So that's a potential extension to our paper. Yeah. Yeah, great idea.
You can, think we can close.
Okay, sounds good.
So I have. Okay, let's, thanks again, Rose.
Okay, thank you. Thank you so much, guys. Great questioning.
And feel free to stick around, like if you have any questions, and it will be a bit more informal. We still have 20 minutes to discuss.
Yeah, I'm happy to do.
Thanks everyone for joining.
Thank you.
Thanks, Rose, again.
Thank you, Pierre.